So let's start with LFortran. In fact, let me open up the issue that we were going to fix. I think it was the constant arrays. So every time something doesn't work, the process is always the same. You copy it, you create a file, you first try to reproduce the error. And you have to compile LFortran or LPython. So I have this LF conda environment. You can look it up in documentation how to create it, and then you just do build 0 and build 1. That's how I do it. I think it works on Mac and on Linux. It should just work. Otherwise, you can go in and just execute the CMake by hand. I will do the same for LPython. And I like to run the test just to make sure everything works. So on the left we have LPython, on the right we have LFortran, and let's kind of test the test file, and we get some error message. So I will now show you how to approach this and how to fix it, or how to go about fixing it. So the first thing to understand about the compiler is the design, and the design is extremely simple. The compiler has a few stages. The first stage is parsing into AST. AST stands for Abstract Syntax Tree. So we'll take an example. We have this very simple program that just computes some expression and prints it. We have the same in Python as well. Same thing. So let's start with LFortran. You can do show AST, which parses it to AST and shows you the result. You can also indent it to see it nicer. And on the Mac, you can double click on a parenthesis and it shows you the other parenthesis, so you can kind of see the nodes. So what you see here is AST. Now let's do the same thing with LPython. Let's do it indent. So you can see the AST is different because Python has different syntax. So you can see each node represents some syntactic feature. Say the declaration here in Python using the annotation is this annotation assignment, I think. In Fortran, the declaration is different, so you can see it's declared here as a node for declaration and so on. So AST is different, but then the next stage is we convert the AST to what we call ASR. ASR stands for Abstract Semantic Representation, and let's do the same thing for LPython. And the ASR is exactly the same for both. The reason it looks different on the screen is because in LPython, the Python source code has this main function that you call, and so it kind of represents that in the ASR too, but the ASR as a representation is identical. So for example, the assignment that's right here on the left and on the right, as you can see, it's exactly the same, or should be the same. I think it is. As well as the declaration. So now we have a symbol table which has information about in this case the x variable. You can see on the left and right, again it should be exactly the same. As well as the print statement also on the left and on the right, and it's exactly the same. So the ASR already is the same. What's different on the left, the main program, it I think calls, it's like calls it, like through a subroutine or through a function. And so the ASR, it has only the semantics. It doesn't have anything about the syntax and doesn't have anything about kind of the differences in the front-end languages, whether Python or Fortran. But it has everything that matters in a way. So it's a symbolic representation of the code. You can think of it that way. Let me kind of load the code again so that you can see it. So if you look at this code, semantically it's equivalent. So you create some expression and assign it to a variable and you print it and you declare it. That's kind of what it is. And that's exactly what you see here. And so it's, as you can see, even the code looks different. And even though Python has slightly different semantics in how things are casted and declared and so on, that's all taken care of by the front end, which means taken care of between the AST to ASR. Once we get to ASR, we get exactly the same representation. Well, and then the next stage is LLVM. So you do show LLVM. And that prints the LLVM IR. So on the right, so the main in LLVM main, or I guess we compile to executable, so main is the first what gets executed, the main program. And you can see if you just look at the function main, it actually I think it's pretty much almost the same. I guess the return is slightly different in here, or I guess okay, on the left the main is here, but it calls this main program and that calls the main 0. But anyway, inside at least it's the same code. Yeah, and that's pretty much it. And so the ASR gets converted to LLVM, and then we can apply optimizations. Let's see if they work. So with the fast, we apply both optimizations at the ASR level, so those that we implemented so far. So ASR to ASR, and then we also apply the LLVM optimizations. And so in this case, let's say on the right, you can see that everything got optimized out, and we just get the main program, and it calls a function print, which is implemented in our runtime library, but it passes 25 to it, which means it already computed the answer exactly and just puts it in. And on the left, as you can see, it actually now it's exactly equivalent, the code, so everything got inlined into the main function, and you can see is literally character by character, this is equivalent. Now on the left you see also some other functions. What happens is that LLVM doesn't know that if these functions will be called from some other place, so it just leaves them there, but they are never called. As you can see, just the main matters. Eventually we should clean it up so that it just produces just the main function. But anyway, so that's all there is to it. And so what we'll do now is we'll dig into the details how to actually fix the issue. Does anybody have any questions so far about the design or anything? So if not, then let's look at the example here, and let's go about fixing it. So the first thing we have to do is figure out which part of the compiler is failing. So kind of a method that first of all, I already know the code, so I know from the stack trace what's wrong. But let's say you don't know, you just do the general approach is you first do show AST. Let's look at the AST, and if you don't get any error, then the bug is not in the parser or AST. Now some of the AST nodes could be wrong in principle, but if they are, we'll figure it out and we'll fix it later. But if it produces AST, it means it produced something at least. Let's try ASR. It turns out even the ASR produces something. Again, it could be wrong, but it doesn't give any error. Let's go to LLVM, and now we get the error. So now we know the error is between ASR and LLVM. And then so let's go back to the ASR. So when that happens, well, in this case it just says constant array not implemented. So what it means is this constant array in the ASR is not implemented in the LLVM. If we do indent so we can see what's going on, let's look up at the program again. So the program just assigns a constant array to a variable, and it's a parameter, so it's a compile time array, or it's assigned at compile time. It's known at compile time, and then we print it. So we can look at the ASR. So there is this array. Fortran is case insensitive, and so we actually cast everything to lowercase so that we can compare things, so that if you type xreal with lowercase, it still works. And then you can see that the array in here looks like it's assigned to the variable, and you can see those numbers are known as compile time, so that looks pretty good. And then the do loop, we don't have to worry about the do loop. That seems to work, but here it is. You can see we are printing the array, accessing. So the ASR looks good, at least at first glance. So it's all in the LLVM, and so now let's go in and see how we can fix it. So the approach I use is I'll typically, if I have the stack trace, I'll launch VS Code, and in here I typically run the example again to fail. And now in VS Code on the Mac you can do Apple, or I guess it's called command. It even tells you command plus click. So when you do that, it goes to the source code. On Linux you can use control. So with the control on Linux you can highlight the stack trace part and goes back to the source code. So let's go one level up. So now we are in the declare vars function in the LLVM backend. So we are in the ASR to LLVM file, because that's the file that translates ASR to LLVM, and we can we have to kind of look around a little bit. So first of all, it's declare var, so it's somewhere when declaring the variables in LLVM that it fails, and it's a long function because it does all the, so it's a local variable that gets declared, and I guess when the symbolic value is not null, which is in our case we are assigning the constant array to it, so it looks like it's only implemented if we assign just a number. But if we assign an array, it goes to that wrapper, and then it's a visitor, and so it fails in this. So this ASR.h file is automatically generated, and in there, if we don't implement it, which means if we don't implement this visit constant array, then then it just gives us an error. And one last thing I should tell you is the ASR, all the ASR nodes are generated automatically from this ASR.asdl file, and in our case the issue is with the constant array, so that's should be some, there it is. It's a node here which has expression, it has the star means a list, so it has a list of expressions as an argument and a type, and then the v, I think in this case it points to, I think it's a variable in the symbol table. So the symbol table is one of these, and in our case the xreal variable is here, and I think it has a symbolic value argument, and the question mark means it's optional, so it can be a null pointer in C++. So if it's a null, it means there is no symbolic value at compile time, but in our case there is, and that's, looking at the code again, it's this this is the symbolic value, I think. So in fact, and then let's say we are not sure about this, so what we can do is we can just verify this. So the symbolic value is 1, 2, 3 is the fourth argument, so let's print the ASR. Let's indent it. So looking at the variable, so it's the first, second, third, and fourth. So the symbolic value is this part. And let's look at let's go to the variable. So that's that array, and I guess there is also a value, and the value, I think, I see. So the symbolic value is not super well documented. We should do a better job, and also in a way sometimes we are changing the design, but I think the symbolic value contains the expression, and then the value is if there is a compile time value of the expression. If it's not a compile time, then it will be assigned here. So in our case we have both. So so the first thing we'll do, we'll override the constant array. We'll create a constant array visitor. So let's look at the constant real, that might be the closest. I'll just make a copy and create constant array. And then, so we look at the constant array. There it is. So it has an argument, list of expressions. In our case, those are the numbers, and a type. So just to kind of see that things work, you can, one approach I like to do is you can, if you throw an exception, it will stop the code here. So I'll just kind of put some, X's there, and I'll comment this out, and let's see if it throws the exception to make sure that it works, that we are in this function. Yeah, so what this says, it that exception got turned into an error, and you can do show stack trace, and it shows you the stack trace in the code how we got to the exception. So here is the line with the exception, and then if you go up, you know, this is previously where it failed. So we are on the, you know, on track. So now we are in here. So then the next thing I like to do is let's print it out to the screen. So let's take these numbers and let's print them out to us just to the terminal. And so now we are essentially extracting information from the ASR, and that's something that you always, whenever, almost everything you fix is either you create the ASR from AST, or you take ASR and you have to extract some information from it and generate LLVM, for example. So let's see. So we'll do a for loop. And then it's the, what was it called? Args. So let's just print. Well, I guess let's start slow. Let's just print the. Let's see if this compiles. Let's see. By the way, this ASR to LLVM is in this libasr directory, and so it's this exactly the same. This whole libasr is the same with LPython and LFortran. So we are implementing ConstantArray here, but we are at the same time effectively implementing it for LPython too. So this worked, and now we can see it printed 0, 1, 2, 3, 4, 5. So that's the index of the file. So 1, 2, 3, 4, 5. Okay, yeah, so that works. And then now we have to access the expression, which is in M, I think args I is the, so we can do it like this. So that's the element. Okay, I guess assigned like that. Should compile still. And then, so then it's an expression. So let's look at the code. It's a list. So now we are accessing every element of it. So now, depending on the type, it can be different types. In our case, because we look at the ASR printout, it's, so the type of the array is real 4. 4 means 4 bytes, like 32-bit real. So single precision real. And in that case, it will be constant, because it's a compile time value. It will be, it should be constant, I think. And I guess this constant array, I guess it's called, I have to think about it. I guess I'm not. It's called on the symbolic expression. So I guess they don't have to be constant. But in in our case they are. So the way I like to do is, I try to implement the kind of most specific case first. So we assume they are constant, and we assume that they are known at you know, compile time, and we assume that they are real in 32-bit, and just kind of get it done in for this particular example and see if it works. And then I try to generalize to kind of cover every corner case and make sure it works in every case. So I can just assume it's constant real. So in that case, this is a list of expressions, so we just cast it. So we'll do ASR downcast. So we'll do constant real, and then we do downcast. Let me admit a few people here. Where was I? Here, downcast. And then, hello. Let's see. EL, I think. Let's see if it compounds. So now, if that element is not a constant real, it will give, this will give an exception. So, and if it is constant real, then we'll have it, and now we can get information from it. So in this case, let's look at the definition. So there is also, this is the definition of the constant real structure, and it has this double, that's the number itself. So that's the number, so we can then print it here. Let's see if it prints. So that would be a good test. Yeah, so it looks like it printed the numbers. So now we have access to the numbers. So we now figured out how to access the array and how to get the numbers out. And now the hard part is now we have to turn those numbers into an LLVM. Effectively, we have to that now you kind of have to understand how the LLVM backend creates the code. And I actually am not super sure myself. And so what we'll do is, I don't know if so we have to assign the result into that internal TMP variable. I don't know if what happens if I just assign a null pointer for now, because we don't know how to create the LLVM. Actually, yeah, I guess it creates an LLVM value. I guess that will probably fail. No, I guess I have to uncomment the. I'm trying to print out how the LLVM looks like so that we can see what's expected. Yeah, it doesn't. What we'll do is I'll keep this exception there. But let's look at the LLVM code to see what we are supposed to generate. And we'll do it. So I think if I comment this out and let's just create a local array of length 5 and not initialize it. Let's see if this works. So this should just print out some random values. In this case, you can see whatever is in the memory. Now let's look at the LLVM code so that we can see. Well, let's look at the ASR first. Let's indent it. So the variable real in this case is just a variable. It's I guess it's an array, so it's 1 to 5. It's a lower and upper bound, but it doesn't have any initialization. And then let's look at the LLVM code. That's the for loop. Yeah, I guess we can start with the for loop. Let's see if we can figure out. So I think the backend kind of keeps the name of the variable so that we can find them here. So it's called xreal, and we have to find how it's declared, I guess. If it's kind of longer, I sometimes save it to a file, like open it in editor. Oh, there it is. So it's declared as, so alloca allocates the variable on a stack, so it effectively becomes a pointer, and then the type of the variable in this case is array and is declared here. So this, what you see is so the LLVM backend represents arrays using a descriptor. So this descriptor is has 1, 2, 3, 4 integers. I think they specify the dimensions, I think, and lower upper bounds, I think, stuff like that. And then the first element here, the float star, that's the pointer to the data, and it has some other arguments. So it looks like if we don't initialize, the LLVM backend already creates the array. It just doesn't put anything in it. What we need to do, I think, is, since the array is known at compile time, one option would be to store it as a global variable in LLVM and somehow initialize it. I don't know but it needs to be stored using this structure, essentially using this dimension descriptor, and it needs to be this array type. I think this is a type. So we have to create an array of this type and initialize it in LLVM. I don't know if LLVM allows it for kind of these nested structures. It does allow it for, let's say, if it's just an integer, then it would allow it. But so if it does allow it, all we have to do is just spit out the definite, kind of create this xreal as a global variable. I mean, create the right hand side as a global constant effectively, and then just assign xreal assigned to it as a pointer. So that should fix it. Now I don't know if LLVM allows it. If it does, that might be a way to do it. If it does not, then we have to I think assign to it. That might be maybe easier. Assign every element to it. And because we know at compile time, as you can see, we know the values. We are accessing it in a loop here and printing it out, and it works. So for every value, all we, in a way, all we have to do is just assign it to the array at the right place. So we could do it right here as well. And we don't even have to do a loop. We can just literally, in here, we can spit out well, so this approach will be a little bit difficult. So this constant array, it returns an LLVM value. So it's being called on the right hand side. It needs to give back some kind of a pointer to the data. So if we want to do what I described, we would have to do it in the upper function. In other words, we would have to do it in I think in here. We would have to kind of go in and see if it's a constant array, and if so, then do a loop here and generate the instructions here. The alternative approach, what I said about the global variable, that should work. In this case, the code here would create some LLVM global constant array if LLVM allows it, and then all we have to do is just get the pointer to it. So and so now we are at the point, I don't know what LLVM does, so or how it does it. So what we can do is, well, now we have to study, and so we can go into the LLVM IR documentation, and we look at the source code. So effectively what we are asking is, is there a way to create a global variable with this type and initialize it in the code? I guess the structure type, I think. And the question is, is there a way to initialize it? So it's a global variable, I guess. So we just kind of search through the documentation. I don't see any example that would initialize it. So typically what I do here is I kind of spend more time reading through the documentation and see if there is an example how to do that. I don't see any right now. The other option is that with the LLVM that I do is you can use Clang and create something in Clang and look at the LLVM and just kind of see how Clang generates the LLVM and what they do. And then the other part, so when you print the LLVM as this code, you have to also figure out how in C++ to actually generate this. And it's not super well documented, and so it's kind of a trial and error. So it's unfortunately a little time consuming, but that's how you do it. So since we only have 10 minutes left, what I'm thinking of doing is kind of wrap up what we've done so far. I'll push it up as a kind of a draft merge request, and then so I'll do it like this. Let's see, and then document how to take it from here.
So in this case, would the equivalent C++ thing for Clang be like a standard array?
I don't know. I don't even know if C++ is something like that. I guess we only need to know how to initialize a struct at compile time. So if there is some C or C++ code that creates some kind of non-trivial struct, any struct, but initialize the members at compile time, and then we can extract how it's done and do it. So yeah, so this shows how to do that. So we'll I guess do right here. So we have to so I'll do investigate LLVM allows initial if so, then create the array using the numbers of a global array, and then take a pointer to it here and return an assign to TP. If it does not, then we have to go one level up, just 2 level, and check if the value is a constant array. If so, insert statements that assign the values to the array. Oops. Effectively yeah, I mean, I think it's clear how to do it. Cool. So it's so I'll create a branch, constant array, I'll just submit it as a merge request. I'll mark it as draft. That should actually compile. It might even pass all the tests, because I don't think this is exercised as a test, because it failed before, so it still fails with this. And then yeah, so I guess so now that's you know, now one has to kind of figure out how actually this should be done in LLVM, and that's always time consuming. It's, you know, it's a big library, and it's a great library. You know, I like it a lot. It does excellent optimizations. That's why we use it, but it takes time to figure out how to do things in it. So yeah, so that's pretty much all there is to it. Effectively, as far as I think the lesson for anybody who's trying to contribute to LPython or LFortran is how to figure out where the error is, and then how to operate on the ASR, how to extract things from it. So I'll kind of review it here a little bit. Effectively, say you are in the LVM backend, so then we are on the other side of ASR, kind of lowering ASR. So in this case, it was a missing visitor, and so it accepts the ASR node as an argument, and then you go into sorry, my zoom is obstructing my. You go into the grammar file and into the ASR to see what arguments you have available, and you find in this case the constant array. You see what the arguments are, so it's a list of expressions and a type, and then in this case we loop over all the list. So you do it so if it's a list, then it has an n, like the number of elements, and then m underscore args are the elements, and they are of type expression, and then you should kind of query the type, but in our case we'll just kind of assume it's constant real, so we downcast it to a constant real, and then we can extract the actual you know, value. And so if you did, like here with this mr, so if you didn't know again what's in it, you can just look it up. So the constant real is here. You can see it has a float r argument and a type, but this r argument, that's the one we are extracting. So if it's a member, it's just m underscore r, and it's a double. So now we have the double, so we have everything we need to know. We don't need to know anything else from ASR. We have all the information, and it's kind of very useful. And so if you are fixing a different bug, you know, it's always, you have to extract the information from ASR, assuming the ASR is correct. And so that's how you do it. And then, what's remaining now is to just generate the LLVM code, accessing these and just assigning them to LLVM. And we don't know how to do it because we don't know what LLVM code to generate in the first place. So we have to now study LLVM and play with that and first figure out what we should generate. Once we know, then it should not be that hard. So yeah, so I think that's in a nutshell. Sometimes you want to fix, I think I would recommend to find some issue or some mistake that happens before, like that gives incorrect ASR. In that case, you would be fixing it in the AST to ASR transformation. In that case, it's this AST, I think it's the common visitor, symbol table, and body visitor. It just to kind of look into some example. Let's say a binary operation. So it visits the AST and then it transforms it into ASR and figures out the types. And so there you operate on the AST, that's your input, and then you have to create ASR as the output. So you don't have to deal with LLVM, so it's a lot simpler typically. Cool, so any questions?
At one point you mentioned that to implement those constant arrays, we have to now make C++ code emit LLVM code.
Mm-hmm.
So where is this thing done, like making C++ emit LLVM code?
That's in this ASR to LLVM. You can see, how LLVM code is emitted here, for example. You just have to call the C++ API of LLVM. And it's not super well documented, so it's a lot of trial and error and reading through the source code to figure out how the LLVM is called. So since we are at the end of time, we can meet again. If you like it, just comment at Zulib, and if you are interested, we can do it again and we can dig into it more. Cool. Thank you so much for your time, and I will see you next time.